I'm Bill Hubsher.
And I'm Lori Meggs. On today's episode of Focus on Marshall, we'll show you the brains behind the new Ares 1X test flight.
But first, we're going to find out how Marshall is using this drop tower to create the next generation of video guidance sensors. We're here in the Flight Robotics Lab at the Marshall Space Flight Center to talk to Jimmy Lee, who is the project's lead for automated rendezvous and docking. And first, Jimmy, thanks very much for joining us. If you would, tell us a little bit about rendezvous and docking and why it's so important to NASA.
Yeah, Bill, when two spacecraft come together, it's real important that everything goes just right. I mean, you don't want those bumping into each other. You got to make sure everything's aligned just right, and the sensors really are a key part to making that all happen. They really serve as the eyes. And so that's really been our focus here at Marshall, is on the sensors and really providing one vehicle, the chase vehicle, the navigation data so it can guide it and they can line the two vehicles up, and you can safely and reliably come in and rendezvous and dock the two vehicles together.
You've been working with some great high technology. In fact, we've got a prototype of what you've been working on here. Tell us a little bit about this particular piece of hardware.
Yeah, this is our next generation advanced video guidance sensor, Bill. It's been being developed and tested here at Marshall Space Flight Center. It's a third generation relative navigation sensor. It actually, some of the key features on this unit are, it really allows you to provide the relative navigation data from 5 kilometers all the way into docking. It can work in a variety of orbital lighting conditions, and it can actually give you the 6 degree of freedom accuracy from 250 meters into docking.
Now, you mentioned this is a third generation, so you obviously have had some of your work flown already.
Yeah, as recently as last year, we actually, our advanced video guidance sensor we developed flew successfully on the Orbital Express mission. It actually was utilized as the primary docking sensor in the first autonomous docking in the history of the U.S. space program.
And that's what this particular piece of hardware here was flown?
This is actually the engineering development unit that we actually use to develop the software and do a lot of the key performance and environmental testing.
Now tell us a little bit about more about how it works. And I think you've got a couple of pieces here that, I mean, this isn't just a paperweight, but it's amazing. It's amazingly intricate.
What you got here is you've got corner cube targets. They're actually what you place on the other vehicle that the sensor actually has to see. I mean, the way our sensor works, it has to be integrated with a target. It actually fires a couple of wavelength lasers. One of those is on the corner cube. One of those is actually absorbed, the other is reflected. It comes back as a spot image that is actually tracked. That gives you the relative position and relative attitude data to allow those two spacecraft to line up and come in and safely and reliably rendezvous and dock.
That can be very precise with something like this.
It really can. It really can. I mean, everything has to be just right, and so you really have to have, a technology that's where it needs to be to make it a reality.
We got lucky here on Focus on Marshall, and the fact that we're actually here on a day you're doing some testing.
We're in the middle of some tests now with our overhead robot, with our dynamic overhead target simulator. And actually what we have here is we have the International Space Station docking port simulator that's actually being transported by the DOTS. It contains our corner cube targets, and we're flying a crew exploration vehicle trajectory, and we're tracking it with our next generation AVGS.
So the next generation AVS, hopefully used on the next generation of space vehicle.
Well, that's what we're hoping for. We think, the challenge out there is not only to be able to have the accuracy that we're verifying, that was previously demonstrated with the AVGS, and we're verifying here in the Flight Robotics Lab with the next generation AVGS, but also to be able to get that extended range out to 5 kilometers. With the next generation AVGS and this skilled team we have in place with Marshall, we've already demonstrated that capability with this ground testing in the Flight Robotics Lab and extended testing with a single sensor that can actually get that relative navigation data all the way from 5 kilometers into docking.
Well, in order to test 5 kilometers, you may need a little more space than we have here at the Flight Robotics Lab, and I think that's where Lori comes in.
I'm here now with Ricky Howard, and he leads the team for the advanced vehicle sensors here at Marshall. And Ricky, you've brought me a long way up. We're 11 stories above the Marshall Center in that neat little steel building that has the meatball on it. I've always wondered what goes on here. Tell me what you do in this building.
Well, we're here because we need to test our sensor, the advanced video guidance sensor, the next generation of it, and we need to test it over long ranges. So we needed a altitude so we can see a long way.
And how far does this go out? You have other targets at other locations, right?
We do. We've got the sensors up here, and then we've got some targets located 2 kilometers, 3 kilometers, and 5 kilometers from here, so we can test at a bunch of ranges
What are you learning from these distances that you're testing?
Well, the sensor is designed to operate at the ranges that the crew exploration vehicle needs to operate for the space station, and so that's 5 kilometers. So we need to make sure the sensor works out to 5 kilometers before we go and build a flight version.
And there are already sensors like this on the space station, right?
There are targets like this on the space station. Corner cube retroreflectors. This is a hemispherical retroreflector. It's got a set of 7 corner cubes so it can be seen from any angle. And we've got pairs of these on 2 different buildings and then a single one on a 3rd building to give us the separation that matches what's on the space station.
So what have you learned so far from all of this?
So far we've learned our sensor works very well. It works all the way out to 5 kilometers and can point out to 5 kilometers as well as actually distinguish 2 separate spots at those ranges. And that's very important if we want to use this to go to the space station.
So it's kind of like our GPS in our own cars, right? You got to know where you're going, and this gives you that little indication, right?
Right, yes. This sensor at long ranges can tell you the range and bearing. It can say 3 kilometers that away. And then once you get close, it can look at a cluster of smaller targets and say the exact relative positions and attitudes and send that back to the spacecraft so the spacecraft knows how to steer.
Well, I would probably need one of these in my car, but they're probably too expensive for you to put in there. Tell us how this fits into NASA's mission overall, though.
Overall, this is a risk mitigation effort for the crew exploration vehicle, and it also has applications to the 2 different COTS efforts that are going on. Orbital Sciences and SpaceX are both going to need to go to the space station, and they will be going to where these retroreflectors exist. So this sensor could be used in that context.
And they couldn't get there without our unique capabilities, right?
That's right.
All right. Thanks, Ricky. It's an exciting time here at the Marshall Center as we get ready for our development test flight of Ares 1 called the Ares 1X. And joining me now is its Deputy Mission Manager, Steve Davis. And Steve, tell me what's going on here at Marshall.
We're very excited. The hardware for the Ares 1X system is being sent down to Kennedy Space Center, and we are getting ready to integrate the system and fly the Ares 1X rocket in 2009.
Tell me, first of all, let's remind folks, if they don't know, what Ares 1X is, and then also why we need a development test flight for Ares 1.
Well, as you say, it's a development flight test. Ares 1 system is a new system, and we're interested in understanding the best way to design it, and so we are going to do a test flight to understand the aerodynamics and engineering of the vehicle.
And specifically today, we're going to talk about avionics. Tell me what avionics are.
Avionics are essentially the brains of the system that allow us to fly the rocket the way we would like. It has both the sensors on it as well as the brains to control the rocket.
All right, and I think Bill's with someone who can tell us a little more about that. Thanks, Steve.
Thank you.
We're here now with Kevin Flynn, who is the avionics manager for the Ares 1X mission. And Kevin, Steve told us a little bit about avionics. If you would give us a little more detail and explain to us why we need an avionics system.
Okay, well, the avionics for this test flight performs 2 functions. It controls the flight of the vehicle and collects the engineering data that we need to support us in the design for the Ares 1 vehicle. You need those functions, obviously, because those are the primary objectives of this test. One of the things we're doing is we're looking to see how does this vehicle fly so that we can learn from that and apply that to the Ares 1 design. The engineering data, of course, gives us the various individual pieces of information we need to also support that design.
So avionics, though, are for primarily test vehicles, right?
Avionics basically control surfaces. In the case of this flight test vehicle, the avionics control the nozzle on the back of the vehicle, telling it what direction to point so that it applies the thrust in the proper direction. It's called thrust vector control.
There's a lot of avionics systems involved in the Ares 1X, but it's also considered a heritage design. Where did you get some of this equipment?
We got this equipment for the avionics system from multiple different places. The primary source is through our contract here at Jacobs. They have subcontracted to Lockheed Martin to get the Atlas V avionics system. That avionics is flight proven, and it is suitable for our test flight here. It is redundant where we need it to be. We also are taking pieces from the avionics that fly on the shuttle today and packaging them for 1X. We're doing a little bit of new development to package things that are normally on the orbiter and putting them on this vehicle. And then we're also getting some commercial off-the-shelf technology for things like data acquisition and transmission of that information.
So, Kevin, how do you test a test system?
That's a good question. The avionics system is basically made up of 2 different types of components. One is the hardware, boxes and cables and such, and the other is software. And we test both of these pieces inside what's called a system integration lab. This is a laboratory where we can hook up all the boxes and cables and software all together and simulate the mission so that we can see how these components perform before we get to flight.
All right, and on launch day, how do you acquire all that data from the avionics?
On launch day, the avionics is operational all the way through the mission, all the way through launch, separation, and recovery. And throughout that time, there are sensors spread out all across the vehicle collecting data. That data is stored on the onboard hard drive as well as telemetry to the ground, so we can get two sources of data after the flight and analyze the mission.
You've got some busy months ahead of you, but we thank you very much for your time.
Thank you.
Bill, lots of exciting work going on with Ares, and I cannot wait to see those test flights.
Oh, me neither. We'll see you next time as we focus on Marshall.